What's up, guys? So, welcome back to Yodamong, and today we are going to design the YouTube. And I want to be upfront about something before we start. YouTube is not one system, it is five, six systems that happen to share a brand. The upload path and the stream path are completely different architecture. The recommendation system is its own beast. The view counter is a classic distributed system problem, and the content ID copyright system could fill an entire video by itself. So, today we are going to cover all of them. We will go too deep in each one of them, and I will tell you exactly where a principal engineer would push back in interview. So, let's start with the functional requirements. What does YouTube actually do? Users can upload video, that is the right path. Then users can watch videos, that is the read path. Users can search for videos, user can see recommendation system to watch the next video, and also see, comment, subscribe. User can see the analytics that are view, watch time, and revenue. Now here's the first thing an interviewer wants to hear. Upload and streaming are not the same flow. When a user uploads a video, you are pushing a large file into a processing pipeline. You do not watch a raw upload. The system has to transcode it into multiple resolutions and formats before anyone can see it. When you see a stream of video, you are actually pulling small chunks of pre-processed content from a CDN. The origin server is almost never involved. Keep this distinction in mind. We will come back to it. Now, the non-functional requirement. At scale, YouTube processes around 500 hours of video uploaded every minute. This is not a typo. 500 per minute. Then availability, streaming must be highly available. Users expect video to play. 5 nines, 99.999% uptime. Then latency, video should start playing within 2 to 3 seconds. That is the user's expectation. Any longer, they leave. About the durability, videos must not be lost ever. This is irreplaceable creator content. The consistency, here is an interesting one. View counts do not need to be exact right in the real time. A video showing 1 million views versus video showing 1,031,000 views, no one cares. Eventual consistency is fine for counts, but for billing and ad revenue, that needs to be exact. So we have different consistency requirement for different parts of the system. The throughput, transcoding pipeline needs to handle massive parallel jobs, and CDN delivery must support millions of concurrent streams. All right, so after this, let's do some back of the envelope math. YouTube has about 2.5 billion active users, and that works out to roughly 80 million daily active users. 500 hours of videos are uploaded every minute. Let's say average video is around 10 minutes long. This is 3,000 videos per minute or 50 videos per second being uploaded. About the storage, a raw 10-minute video in 1080p is roughly 1.5 GB. But after transcoding it into multiple formats like 4K, 1080p, 720p, 480p, 360p, and the multiple codecs like H.264, VP9, AV1, that multiplies to around 10 GB per video. 3,000 videos per minute times 10 GB is equal to 30 terabytes per minute of new storage needed for uploads. Now per day, this is around 40 petabytes. If you want to read, YouTube serves about 1 billion hours of video per day at an average bitrate of 2 Mbps. That is 2 times 10 to the 15 bits per day of outbound bandwidth. This is why CDNs exist. No single data center can serve this. Database writes, if you want to assume 50 uploads per second with metadata for each video, the title, description, tags, creator status, that is manageable in a relational or document store. Now, view counter writes are the spiky case. A viral video can get millions of views per minute. A naive counter increment in a database would serialize all those writes. We will address that in the deep dive section. Now, after this, let me sketch the core APIs before moving into the next section. The APIs are very important. Because of this only you are able to access all the videos. In upload APIs, we will have 3 APIs. One is the post API to initiate the upload. The second is the upload URL. This is multi-part upload directly to the blob storage. This does not go through your application servers. It goes directly to the object storage. Then we have post videos and the video ID and publish. Once the upload is completed, it triggers processing. After that, we have the streaming API. We have this get API, which is V1 videos, video ID, and manifest. It returns the HLS or dash manifest file. This tells the client what all resolutions are available and where to find the chunks. The client then fetches the chunks directly from the CDN. Then we do the get V1 video, video ID, and metadata. That is for title, description, like count, and comment count. The other part, we have search API, where we can provide the query and the query parameters. We have the feed, which gives the recommendations for the video we want to watch. Then we have interaction APIs, which tells about the views, which increments the view count. Then we have the video likes and then video comments, which tells about the comments and the likes. Okay, after doing the API, we need to also discuss the data model. This is very important. It will tell how the data is stored in the databases. And this is very important. If you don't discuss this during the interview, you're missing a lot out. And the interview will never tell you to tell the data model. They will implicitly want to know about it. So we have the video table. In that, we have the video ID as the primary key, then the creator ID as the foreign key. Then we have some text like title, description, status, raw storage key, then duration sec, created at, and publish time. Then we can have the video rendition tables. One video has many rendition types after transcoding. So we can have the rendition ID, then the video ID. We can have resolution, in what resolution it is, like 1080p, 720p, 580p. Then we have the codec, then bitrate kbps, the storage path, manifest URL, and the created at time. Apart from that, we will have the user table, that is a standard user record. Then the channels table, a creator's channel. One user can have multiple channels. We have the subscription table, users to channel the relationship. This is a many-to-many join table. The view events table, this is a feed analytic table. You do not store view count as a single row as you increment. You store the events, then you aggregate them. So here is the view. We have event ID, video ID, viewer ID, watched ID, watch duration, and the session ID. Then we have the comments table. These are the nested comments which needs a parent comment ID for the thread structure. So that's why we will have a comment ID, video ID, author ID, then the parent ID. It can be nullable. Parent ID is the parent comment, then body and the created at timestamp. Now let's talk about what database to use for each of them. Video data and the user data. We can use a relational database like PostgreSQL or MySQL. You have the foreign keys, you have the transaction, and you need strong consistency. Then we have the view events. This is a time series data and it is used for analytical store. So for that, we can use ClickHouse, Apache Druid, or BigQuery. You're doing aggregations over the time window. So OLAP and not OLTP. For the comments, it could be either relational or a document store. MongoDB works here, I suppose. Then for the search, we can use Elasticsearch. It can do full text search with ranking. For recommendation, a dedicated ML feature store plus a graph database or embedding stores. Okay. After doing the details around the periphery, we will enter into the high-level design. Let me walk you through the high-level design now. There are two major flows. One is the upload feature and another is the streaming. Let me explain them to you separately. We'll start with the upload feature. Now, a creator hits the YouTube web app or the mobile app. They select a video file. The client calls our upload service to initiate. The upload service generates a signed URL pointing directly to the raw blob storage. Think of like Google Cloud Storage or S3. The client then uploads the video directly to the blob storage. This bypasses your application servers entirely. The file can be of hundreds of gigabytes. You do not want that traffic touching your API layer. Now, once the upload is completed, the blob storage emits an event. This event goes to the messaging queue in Kafka. The topic is something like video.uploaded. Transcoding job scheduler picks up the event then. It creates the transcoding DAG, a directed acyclic graph of jobs. The DAG looks like this. Stage 1, validation. Check the file is a real video file, not corrupted, not virus, and acceptable format. Then stage 2 is the split. The video splits into segments. Let's say 10-second segments. Then stage 3 is the transcode. Each segment is transcoded in parallel into multiple resolutions and codec. This is the most expensive part. You are spinning up hundreds of workers. After that, we have stage 4. Stage 4 is assemble. We assemble the transcoded segments back together as per their resolution. Stage 5 is the package. We generate HLS dash benefits. HLS uses .m3u8 files, dash uses .mpd files. Then at last, stage 6 is distribute. We push the transcoded files to CDN origin nodes. After DAG completes, the video status in the database flips from processing to published. The creator gets a notification then. The video becomes visible in each search and the feeds. The next flow we'll discuss is the streaming flow. Now, this is completely different. When viewer clicks on the video to play, the client calls the manifest service. The manifest service looks up at the rendition tables, finds the available resolutions, and returns a manifest file. It could be an HLS or a dash. The client reads the manifest. It picks a starting resolution based on the current network speed. The adaptive bitrate algorithm then adjusts up or down as per the stream progresses. Then client fetches video segment directly from the CDN. The origin server is not involved. These are the static files sitting on the CDN edges nodes around the world. The CDN is the most important component in the streaming part. YouTube uses Google's own global network, not a third-party CDN, but conceptually it works the same way. Videos are cached at edge nodes close to the viewer. A video in Seattle is cached in the Seattle edge node. Someone watching from Portland hits the Seattle edge. Latency is in milliseconds. Now here comes the tricky part. For a viral video, a new video that suddenly gets 10 million views in an hour, there is a warming strategy. The system pre-pushes the video to many CDN edges proactively. It monitors the view velocity. When view velocity crosses a threshold, it triggers the CDN. For long tail videos, videos that get watched once per week, those videos might not be at the nearest edge. They are fetched from the origin on first request and then cached locally. Now, here is one very important part, that is adaptive bitrate, HLS versus dash. Now, let me spend a minute on this because the interviewers love to ask this question. HLS is HTTP live streaming. This was invented by Apple. It is a standard on iOS and Safari. Dash is dynamic adaptive streaming over HTTP. And this is an open standard and it is supported everywhere else. Both work the same way conceptually. The video is split into small segments, usually 2 to 6 seconds each. A manifest file lists all the available quality levels and points to the segment files. The client player monitors the download speed. If the last segment downloaded slowly, it steps down to a lower bitrate. If it downloaded quickly, then it steps up. The difference between HLS and Dash is in the manifest format and the codec flexibility. Dash supports more codecs. HLS is dominant on Apple devices. The YouTube serves both of them. All right, we discussed about the high-level design. We need to deep dive now. And this is the most important part. So please concentrate very well over this one. The interviews are more interested in the deep dive component than the high-level design because they want to drill deeper. Okay, guys. Now, first we will start with the component of transcoding pipeline. Now, transcoding is a CPU-intensive application. Encoding a single 4K video into H264 can take up to 30 to 60 minutes on a single machine. So, YouTube does not transcode each video serially. It parallelizes it into two levels. Level 1 is split by segment. A 60-minute video becomes 360 10-second segments. Those 360 segments can be transcoded on 360 different machines simultaneously. Level 2 is split by rendition. Each segment is transcoded to 1080p, 720p, 480p, 360p in. This turns a 60-minute serial job into a job that completes in minutes. Workers pull segment resolution pairs from a queue. Each worker transcodes one segment at one resolution. When done, it marks the task complete and pulls the next one. The scheduler tracks the tag. When all the segments at all resolutions are done, it triggers assembly. The transcoder workers needs to be elastic. A viral upload can mean 10,000 segments suddenly entering the queue. The worker pool auto scales using something like Kubernetes horizontal pod scaler or a spot instance fleet on a cloud provider. The codec choices also matter here. NH264 is a universal baseline. VP9 offers better compression at same quality, about 30 to 40% more smaller. AV1 is much better, but encoding is slower. YouTube now encodes popular videos in AV1 to save the egress cost. Then we have the sharded counters for views and likes. Let me talk about the view counter problem. A viral video gets around 1 million views in an hour. This is 280 views per second, all trying to increment the same row in the database. In a naive implementation, you have a views column on the videos table. Every view is updated by doing update video set video view is equal to views plus 1 where video ID is equal to X. At 280 requests per second, you have a lock contention. The database becomes a bottleneck. The solution is sharded counters. Instead of one counter, you have n counter shards. When a view event comes in, you pick a random shard and increment it. To get the total, you read all the n shards and sum them. This distributes the right load across n database rows or cells. The lock contention is reduced by a factor of n, but you still might not want to write to the database on every single view. Instead, you buffer view events in memory or in Redis. Every few seconds, you flush the buffer to the sharded counter table. You lose at most a few seconds of precision. That is totally acceptable. Now, for exact analytics, the ad revenue attribution, you need every event. Those go into the event stream in Kafka. And these are consumed by the stream processors like Apache Flink and land in an OLAP store like ClickHouse for the precise aggregation. Okay, so now we will discuss about the recommendation system. This is also very important, one of the most important and one of the most happening system right now, especially when the AI system are on the verge and on the rise nowadays. Now, this is where YouTube's business lives. The recommendation system has three components: candidate generation, ranking, and re-ranking. You start with the entire catalog of videos, hundreds of millions. You cannot score all of them, so you must use a fast model to narrow down to a few thousand candidates. Now, this is often a two-tower neural network. One tower for the user, one tower for the video. You compute embeddings for both and find the closest videos in the embedding space using the approximate nearest neighbor search. After that, we do the ranking. You take those few thousand candidates, score them with a heavier model. This model considers the watch history, the click-through rate, watch time, freshness, and diversity. The output is an ordered list. After that, we have re-ranking. Now, business rules are on top. Remove videos the users have already watched. Ensure diversity, not 10 videos from the same channel. Apply content policy filters. Optionally, you can inject promoted content also. The training pipelines run continuously. Every watch, every click, every skip is a signal. The models are retrained daily and more frequently using the signal data. In the feature store, the model needs feature at the serving time. Users' recent watches, videos, historical click-through rate, and the time of the day, these are pre-computed and stored in a feature store. Think Redis of hot features, Bigtable for historical features. Next system is the Content ID copyright system. This deserves a mention because it is architecturally very interesting. When a video is uploaded, the YouTube generates a fingerprint of the video and the video tracks. The fingerprint is compared against a database of copyrighted content registered by the right holders. The fingerprinting is perceptual. It must survive the compression, re-encoding, pitch shifting, cropping. It is not a simple hash. If a match is found, the right holder's policy is applied automatically. They can block the video, monetize it with the ads, or track the analytics. This happens without any human review. The fingerprint database had hundreds of millions of reference tags. Matching a new upload against this is a fast approximate nearest neighbor problem. Similar to the recommendation retrieval step. Now, if you're interviewing for the staff or principal engineering level, there are some of the questions which you must consider before going ahead. They can ask you about the transcoding pipeline is eventually consistent. So if a user uploads a video, it is not immediately available. What happens if the transcoding job fails halfway through? Then they can ask about the CDN cache invalidation. When a creator deletes their video, how do you ensure it is removed from all the CDN edges? Another question that can come is YouTube's recommendation system optimizes for a watch time. Now, what are the second order effects for this, and how would you architect the system to mitigate them? Another question, how does YouTube handle upload at the network edge for creators with the poor connectivity? And if you need to support 4K and 8K streaming globally, including in the region with the poor internet, how do you design for this? All right. So these were some of the questions. Maybe you can, go back to the chat GPT or search about the answers. You can obviously get about these, but these are very important questions. Next is we will talk about the observability and the monitoring. So let me talk about how you monitor the system in the production environment. You need metrics at every stage of the upload and the streaming pipeline. In the upload funnel metrics, we need to do upload initiation rate, then upload completion rate, then upload abandonment rate, then the user who start but do not finish, transcoding queue depth. It tells how many jobs are waiting, then the transcoding job latency, the P50, P95, P99 time for uploading the video to complete publishing. Another metric can be the streaming metrics, where we talk about the playback start latency, the buffering ratio, the bitrate ladder utilization, where we decide what percentage of views use 4K versus 720p versus 360p. Then we can talk about CDN cache hit rate. Too high origin request rate means CDN warming is not working. We can talk about transcoding worker utilization. Here we talk about how many workers are idle or overloaded. Then we can talk about the queue depth per topic in the Kafka. And also we can talk about the database connection pool utilization. For alerting, you want SLO-based alerting. Not CPU is at 80%. That does not tell you if our users are impacted or not. Instead, the playback start latency P95 has exceeded 3 seconds for more than 2 minutes. This is what we want to know. So this is a user impacted threshold that pages someone, and this should page someone. Then we have distributed tracing. Each video uploads gets a trace ID. The trace follows the video through the upload, transcoding, packaging, CDN push, and first playback. When a creator says my video is stuck in processing, you can actually look up the trace and see where exactly it has got stuck. All right, let's recap what we have covered today. We noted that upload and streaming are separate architectures. We never conflate them. The transcoding pipeline is a DAG, parallelism at a segment level and rendition level. HLS and Dash are both served. The adaptive bitrate picks the quality dynamically. CDN is the critical path for streaming. Origin is barely involved. Now, shared counters solve the problem of viral video write problem. The event streaming handles the analytics for us. We discuss about recommendation system, which has a 3-stage pipeline, the candidate generation, ranking, and re-ranking. Then we talked about the content ID, that is perceptual fingerprinting at massive scale. We also talked about some of the principal engineering level questions. We talked about the upload pipeline, the streaming, CDN cache hit rate, then recommendation system, then view counting. Now, this is the YouTube system design in full depth. If this was useful, please subscribe for Yoda Monk. I will release the next system design deep dive next week. See you till then.